Hey everyone, and welcome to the SaaS developer community, where we learn from each other how to build software as a service. And I'm here alone today, and I wanted to talk to you guys about transactions, which are obviously very important when writing any kind of stateful service, which honestly most SaaS is kind of stateful. So the original plan was to talk to you about transactions in distributed systems. And the reason for that is that I presented at QCon last week, and I talked about serverless databases and cloud-native databases, and these databases are usually distributed by definition. I talked a lot about them, but I felt I didn't quite do the transactions topic justice. I slightly hand-waved it. I showed some transaction coordinator. I said, okay, there is Twophase commit, there is Paxos, there is Raft, there's all those protocols. I didn't really explain any of it. So I said, okay, I'll take the time today to explain it. And then I realized that transactions are kind of complicated, even if you don't talk about distributed databases. And there is a lot of nuances and guarantees. And when I talk about transactions, what exactly am I talking about? Because it's hard to say that, okay, this distributed protocol preserves those guarantees, doesn't give you the other guarantees, if I don't even talk about any kind of guarantees that you get, from a normal database like Postgres or MySQL running on a single machine. So I switched my plan and said, okay, let's start by just talking about transactions. I'll focus mostly on transactions on a single machine. Toward the end, I'll hand wave again around transactions in distributed systems. And maybe in a few weeks, I'll get back to talking just about transaction in distributed systems, and we'll make it a two-part thing. So we'll talk about transactions. What I basically mean is something along those lines. You want to move money from one bank account to another, and you really want the whole thing to happen, or none of it to happen. What you really, really don't want is to be left with half a transaction. So transactions kind of guarantee that those series of operations happen as a single unit. This is the basics of what you need in a transaction. Now, most of us are not doing banks, but all kinds of systems. If your SaaS does something like linear and you want to update one of your tickets, and usually when you update the ticket, there is a series of things that you want to happen as a result, and you want them all to happen together or not to happen at all. And the properties that I just talked about is atomicity. The idea that something either completely happened or did not happen at all. That you do not have half a transaction. This is, you treat a transaction as a single atom. This is the atomicity guarantee. Now, atomicity is really the first part of ACID, right? The basic guarantees of transactions in most relational databases today would be atomicity, consistency. In ACID case, and this is important, in ACID case, consistency really means complying with foreign keys constraints. And if there is a relation between the two tables, because it's a relational database, make sure that your transaction does not leave the database in a state where those relations and relational constraints no longer exist, that you have a child table that is supposed to reference a parent, and the parent actually doesn't exist because of something in the transaction. So that's consistency. Note that it's very different from consistency in distributed systems, like in the CAP theorem, which means things like, I wrote a bit of data, and now I'm trying to read it back. Can I actually see it, or was there a network partition and it's gone? So consistency, isolation, which I'm going to talk about a lot, so I'll skip for a moment, and durability. Durability basically means that once a transaction committed, it's actually persisted to disk, often to more than one disk, usually to, at the very, very least, multiple copies of a transaction log or a write-ahead log. The idea is that once it's committed, you should expect to continue seeing the result of the transaction, no matter what crashes, no matter what happens to the database. Isolation is the tricky bit. What does it actually mean for transactions to be isolated from each other? Well, usually isolation is all about the database concurrency controls. You have multiple transactions running at the same time, committing things. What does each transaction see? And there is a lot of different ways to look at it. Back in 1992, the ANSI committee decided to define different levels of isolation. And the way they did it is extremely controversial to this day. Like, it's one of those things that everyone says it's useless, and then everyone is also keeps on using it like nothing happened, and they keep on using it because everyone else is using it. So we're kind of stuck with this forever, even though everyone knows that this is very problematic, as you'll soon see. So the idea was that they started by defining the logical ideal of isolation. And the logical ideals of isolation in the context of concurrency controls, transactions happening at the same time, is that if transactions happen at the same time, the result of all those transactions happening should be something that is possible to achieve if each of them ran in a different, one after another. We don't say which one should run first and which one should run second, but we promise you that after all those committed, you will have a state that is achievable by some kind of serial ordering. This is why it's called serializable. You could find post facto serial orders that achieves the exact same result as those transactions. Why is serializability so good? It means that you can reason about things. You can say, okay, I'm going to let's say that you have some kind of invariant, some kind of guarantee that you always want your application to keep. You don't have to think about all possible combinations of transactions. You can imagine, okay, this transaction ran and I know it preserved this guarantee. And then the other transaction ran and it preserved the guarantee. And you can kind of put them in a series and reorder them. And as long as every transaction preserves your guarantee, even if they run in parallel in the real world, you still know that your logic holds. So it really is super important if you need to reason about your system. Unfortunately, this is kind of ideal. Back in 92, it was very obvious to everyone in this ANSI committee, which had all those important database mavens, it was very obvious that you cannot achieve good performance and serializability. Turned out, spoiler alert, later not to be true, but that's what they thought. So they said, okay, let's leave few more levels and explain what can happen if you do not have serializability. So they said, okay, we have a list of some bad things that can happen if you don't have serializability. You can have phantom reads, you can have dirty reads, you can have non-repeatable reads. And then let's define the other levels as some of those bad things may happen. And this sounds reasonable because you say, okay, I'm okay with some bad things happening and I want more speed. Let me go with read committed. Yes, some bad things may happen, some other bad things might not happen, and I know what they are, so I'm okay with it. So the first thing that every responsible person writing an application with transactions is to understand the bad things that can happen and how to prevent them. Okay, bad things that can happen, number one, is dirty reads. What does it mean, dirty read? It means reading data that has not yet been committed. And remember, if it's not committed yet, it may be that it will never get committed. I mean, the developer may change their mind and roll back the transaction. The machine may crash. Like, who knows what will happen? That's the whole point of not committed, is that it's not durable. The data may go away. So in this situation, let's say that I create a new bank account with some balance and I allow dirty reads. This means that someone else who does select star from accounts may see the account. That transaction may later get aborted due to an error. It may get rolled back. But whoever ran this report thought that our bank has one extra account with one extra $100. You will have bad reports. Now, it sounds so obviously terrible that you'd say, who in their right minds would ever do dirty reads? And the answer is me. So back in 2000, this was absolutely the beginning of my career, and it's 23 years ago. So now you know exactly how old I am. I started my career, and in that job, I actually worked on one of the most interesting systems that I had the pleasure to work with. It was imagine a very early version of, let's say, Datadog or Pingdom or something like that. It was a software as a service, and we had all those agents all over the world, and you can tell them to monitor our customers' websites. They monitored all those websites, and then they sent how fast or slow, or if there was any HTTP errors from all those websites back to our backend, and then our customers could generate report. Now, as the service grew, that was a very, very write-heavy database. And we started getting logs, we started getting contention. Remember, it was also a very early version of either SQL Server or Oracle. I don't even remember which one it was, very early on. And, well, we didn't like it. We wanted our services to be scalable and be fast. We turned on dirty reads. We allowed for dirty reads. And the reason was that it was write-heavy, and all those were just, pings or HTTP gets. If you saw an HTTP get that you shouldn't have seen, the chances that they would actually roll back or get aborted were virtually nil, very rare. And the impact of seeing one bad transaction or one thing that actually turned out to not exist later was not a big deal. We knew what we were getting into. We accepted this risk. So these days, I don't think if you need this kind of, I don't care what's happening and I just need it to be fast, there is a lot of options that are not a relational database, and you'd probably go with those. So you wouldn't do what we're doing. And therefore, it's extremely rare to see relational databases used that way. Although, these days, sometimes people just want to do everything in Postgres. So maybe, who knows? Okay, the second thing that... bad things that can happen is that you'd see data that was committed but changed in the middle of your transaction. So this is called non-repeatable read, and it can happen in a read committed isolation level. And the idea is that you started your transaction, you did select star from accounts, and you got some result. Someone else started their transaction, updated the accounts, committed, and you're somewhere later in your transaction doing the same select again. You will now get different result. It is correct and true, but it is different. Now, is that okay in your system? Sometimes it is, sometimes it isn't. You're the only one who can know how it will impact your logic. If you're running a lot of selects and they're supposed to, and updates and inserts and creating temporary table, and you're supposed to create at the end of the day a single report, this can be kind of catastrophic because the report itself will be inconsistent. There's always this manager that says, well, why am I seeing 500 here, but the other one only says 200? And if you say, well, it was two different selects, you kind of look weird, like they want a report that makes sense in a specific point in time. I think this is even the default in most databases. So unless you have a reason to do something different, this very well may be something that you currently have. Next big bad thing that can happen is that you have repeated reads isolation. So repeated reads isolation is a good thing. This basically means that you don't have the error from last time where the value changes in the middle of the transaction. Every value that you read will be identical, but you can have phantom reads. What are phantom reads? Let's say that, again, you start your transaction and you're doing a select, and you get all the data from all the accounts. Now, someone else begins their transaction, does an update, does an insert, that's what is new, and then commits it. Again, a bit later, your report is making progress. A bit later, you do select from accounts again. In repeated reads isolation level, you are guaranteed that all the values you've already read will be the same. So you will see for account 1, 2, 3, the exact same balance in both selects. Let's say it was 200 in the beginning, even though there was an update setting it to 500, it will still be 200. So this is fine. But phantom reads mean that you will get extra value in the second select. The first select got you account 1, 2, 3 with the old balance. The second select gets you account 1, 2, 3 in the old balance. The first select did not see account 1, 2, 3, 4, 5 because it did not exist. The second select will see account 1, 2, 3, 4, 5 because it was committed and now it does exist. Yeah, sometimes acceptable. Sometimes someone will like, why do I have this number of accounts here and not this number of accounts there? It all depends. Okay, so this is a bit weird. Why do we have this level that allows me to have something that is very static at a specific point in time, and long as the values already existed, but then new values will just show up? And the reason is that the way back when all those bad things were kind of considered and the committee had these conversations, allowing this kind of thing was actually kind of a solved problem. Everyone knew how to do it, and the idea was that whenever you select something inside the transaction, you take a lock on it. And this lock does not block other readers, but it will block writers. So this is readers block writers situation. Now, the idea is that you don't want to take a lock in the entire table. What if you only read one row? It's a gigantic table and you lock the entire system. So the idea is that you lock only rows that you actually read. Well, if you lock only rows that you actually read, you cannot possibly lock or prevent any new rows, which means that the next select will see new rows that got added. So this is completely backwards, right? I mean, they kind of took an implementation detail and turned it into the standard for isolation levels. And then new systems showed up, multi-version concurrency control, MVCC, and a standard implementation showed up for those, which is taking snapshots at the beginning of transaction. So you basically only see data that was frozen to the beginning of a transaction, essentially. And in those scenarios, it's actually not that hard to ignore inserts, because those inserts will have a later transaction ID, right? My transaction started first, it will have transaction ID 200. The second transaction, the one that did the insert, will be 201, let's say. When I do the second select, I can see that, hey, the new row actually has the minimum transaction ID. The first transaction that ever inserted it is 201. I'm 200. I should not see it. And this is what normal databases do these days. So it's kind of weird. It basically makes the whole thing kind of weird. But we have serializable, where none of those bad things can happen. So we're all good, right? Well, it turned out that defining a perfect state and then defining some states where bad things can happen has this logical issue in it, which is there may be bad things you didn't sort of think of. So, yeah, the whole thing is kind of, I think a lot of people, like it took basically 3 years from the point where ANSI said, hey, this is the list of perfection and then levels in which we allow some bad things to happen, until smart guys from Microsoft said, you guys missed some bad things and we need to rethink the whole idea. And they came up with this entire table. A lot more bad things can happen. You have a cursor with lost updates. You can have fuzzy reads. You can have read skew. You can have write skew. And like, okay, can we have more isolation level? Do we need those? Here's snapshot isolation. Some databases have snapshot isolation and call it serializable. People believe it's serializable for marketing reasons. They will never change their mind. And some databases actually call it snapshot and they want to introduce real serializable. So you have all those weird considerations. If you're using Postgres, for example, the way they solved it is that they listed the standard bad things, and then they made some extra notes. First of all, they added a column for serialization anomaly. What is serialization anomaly? Well, it's extra bad things that can happen. Things like write skew, which is where perfectly legal transactions with snapshot isolation end up swapping values in a way that you couldn't really ever get if you just ran the transaction serially in any order. So they basically sat down and figured out a way to implement real serialization fairly efficiently, not perfect, but they came up with a way to do it. The problem is not always just efficiency of checking for serialization. It is also the fact that in serializable mode, a lot of things that are actually legal in other modes will be illegal. Even some things that are actually legal through serializable may be illegal. So it is actually fairly conservative, but it absolutely guarantees that all those bad things, including the stuff that in 1992 nobody thought about, none of those are going to happen. So that's cool. They also make a note that repeatable reads in their case does not actually allow for phantom reads because they're using this snapshot isolation that I just mentioned that can actually validate that the rows are not new. So as I mentioned, it is fairly complex. A lot of bad things can happen. Smart people in 1992 thought of some bad things. Bad things happened later. Depending on your database, serializable may not mean the same thing. It may mean serializable in let's say Oracle can mean more or less the same as repeatable reads in Postgres. So you kind of have to read the fine print on those and really understand the bad things and make good decisions around it. And remember all of this, and we are still only in a single machine. The main problem in distributed systems, well, there's two. First of all, there is multiple copies of the data. And if you read the wrong copy or you write the wrong copy, which can happen under all kinds of network conditions, bad things will happen. The other thing that could happen is that time in distributed systems is complex. Remember that each machine has its own clock and they will never be perfectly synchronized. So writes on one machine may happen logically in the past when something else happens concurrently in another machine. And reasoning through that is an entirely new can of worms. But I do want to point out the source of the problems. So remember what serializable means. We don't care what is the result, as long as there is some ordering of transactions that is sequential that could lead to the result we are seeing. And it turns out that this definition made assumptions that are so obvious in a single machine, for example, that time only advances in one direction, that they didn't even think of spelling out some sequential order that has time limits on it, that is within a reasonable period of time. Like all those things, they didn't even consider it because in a single machine, it's just you take stuff for granted and then you're in distributed system and you no longer take stuff for granted. Now, again, the people who in the ANSI SQL committee should have done better. They were highly paid professional. Distributed systems did exist back in 92. They could have done a bit more reading about it. So I don't want to make too many excuses about it, but the fact is that to this day, if someone tells you that your distributed system is serializable, it is just not enough. Okay, let's look at one example in which two examples where bad things can happen. The first one is that we are updating the same account twice with some time difference between them. So those are two separate transactions not happening concurrently. So let's say that we are updating account 123, and the first transaction updates the balance to 500, and then, I don't know, this commits, it's all good. You even check the account, you do have $500 in this account. You wait a few minutes, update again, now you set it to 200. Not exactly a realistic scenario, but bear with me here. So you set it to the same account now to 200, you commit again, and you check. What does it say? It says 500. Interesting. You try again, you commit again. You check, still 500. What's going on here? Serializable says that every result is okay as long as there is some order of transactions that allow it. The order which allows you to see what you're saying is the order in which all the updates that set the balance to 200 happens before the update that sets the balance to 500. So you kind of time shift those amounts back into the past, and it's always somewhere in the future it's going to be 500, which is extremely weird, that there is something happening a lot in the future, but it's not. And the thing I just described is a bit extreme, that you keep trying and it's always happening. But if you have a distributed system where last write wins and the clocks are not perfectly synchronized and you have network partitions, you could have something that physically you looked at the clock, it happened later. Logically, in this database system, it was shifted to the past, and as a result, your write was completely lost. So that sucks. But wait, it can get even more fun. Let's say that we have two bank accounts, both belong to us. We want to move some money between them, but we're doing it in a way that banks normally do, which is to move money between them through an account that the bank actually owns. So instead of me moving money directly to my account in one transaction, there is one transaction moving money from my account to the bank and another from the bank to the other account. This seems fairly innocent, but note that the first transaction, after it completes, it basically acts as a cause for the second transaction. If I didn't do the first one, the second one would never exist. So there is kind of a cause and effect relationship or a dependency. Transactions, by the way, are huge on dependency graphs because you write a value and then someone else reads it, so it creates this chain of dependencies between different transactions. In this case, the second transaction obviously depends on the first one, but because we allow things to happen in any order, especially if they never happened concurrently, but regardless, the second transaction could actually happen before this first one. Now you're thinking, well, what's the big deal, right? I mean, as long as we have a guarantee that both will happen, like it's fine, right? In this case, I don't have any perpetual rights in the future. It turns out that it's not fine, because if you switch the order, there is a point in time when both of my accounts put together have a balance of $1,000 in them, where it should have only been 500. And this matters if, let's say, you use this information to approve loans or something like that. It kind of starts mattering. So time travel can be extremely dangerous, and it's something that can be an issue in distributed systems. So in order to reason about transactions and especially isolation in distributed systems, it's not really enough to just look at the normal ACID guarantees. You have to look at the same time at all those distributed system guarantees around time bounds, eventual consistency, read after write consistency, all those other things that are very complicated in their own right. This is from a Jespen blog post. I linked to it. But the idea here is that you basically have strict serializable, which is both serializable in the sense we just discussed, and linearizable, which defines the interaction between transactions that are also replicated to different machines in a distributed system. So you can see this, there is an entire tree of different levels of guarantees you can have in distributed systems. You have this entire tree of guarantees that you can have in between concurrent transactions in a single system. And over here, it's kind of an attempt to put them together. Obviously, it's not the only way to put them together. There's different systems. Some of them are used in production, actually fairly good. You can actually reason about them in different ways, and they are not strictly serializable, or they may be strictly serializable on subsets of the data, but not in every situation. And the last thing that I really want to leave you with, because I think this kind of drives home how much you have to go through to really understand your distributed system. A lot of people talk about two-phase commits. Oh, how do I do transactions in a distributed system? Well, I do transaction in one system and then I do a two-phase commit to synchronize it with a transaction on another system. And it's important to know that two-phase commit doesn't touch any of what I just talked to you about. It doesn't guarantee any level of isolation whatsoever. It guarantees atomicity. only the first thing that we said, that when you move data between two bank accounts, if you have two-phase commit, you can, and you have bank account 1 on machine 1 and bank account 2 on machine 2, you can be 100% sure that at the end of the transaction, the money either completely moved to the other machine or not moved at all. What you really cannot guarantee is what happened when someone else ran a select star and tried to read all data from both databases, and he may have seen money in neither account, he may have seen money in both accounts. No guarantee. Two-phase commit does not guarantee you any of it, which is why you need, it's knowing that the system is two-phase commit is absolutely not enough. And having stronger guarantees means that you need to do things like synchronize the transactions between the snapshots, like what transaction ID it is, what came before, what came after. You have to really synchronize time between different machines, which is where ideas like linear reliability, vector clocks come into the picture. So at least now you know what you don't know. And if you're on a single machine, I think I presented at least some scenarios that allow you to reason about how your transaction work and which level of isolation you want to work in. So hope you enjoyed it. See you guys next week.